So today we are starting the 15th non-associative day in online seminar. And today our first speaker is Dr. Zhanqiang Bai from Soochow University, China. Then the title of the talk is Gelfand-Kirillov dimensions of highest weight models of simple Lie algebras. So I see that our speaker is here.
Yeah.
So, Dr. Zhanqiang Bai, you are welcome. So
Thank you.
Can start your presentation.
Okay, thank you. Thank you for the introduction. Can you see my screen? Maybe I...
Yes.
Yes, it's okay.
Okay. Thank you for the introduction. And today I will talk about the dimension high-weight module for some simple Lie algebra, especially for the example type Lie algebra. By the way, I'm working in China in Suzhou University. Suzhou is a big city near Shanghai. So I will give the definition for J dimension and then talk about the J dimension of high-weight model for classical Lie algebra. And then I will talk about the dimension of high-weight model for exceptional Lie algebra. This concept is originated from 1960s, and that time Gelfand and Kirillov, they introduced a quantity to measure the rate of growth of an algebra in terms of some generating state. So now we call it Gelfand and Kirillov dimension. And later on, in 1970s, David Wogan and Anthony Joseph, they used the Gelfand and Kirillov dimension to measure the size of some infinite dimensional representation of Lie algebra and the Lie groups. There are two papers talk about some basic properties about J dimension. The first one is from Joseph, and second one is from Wogan. Wogan focused on the Haushana model of Lie groups. And in 1985, Lusztig found that the J dimension of a regular integral high-weight model can be computed by using the A function on work groups. And then in 2019, and with my co-author Xunqi, we found that we can generalize the Lusztig result to compute the J dimension of any high-weight model type A. We only use the Robinson-Shented insertion algorithm. And after 4 years study, we found that we can generalize our algorithm to type BCD, only use the RS algorithm. And later, during this process, actually, I sent some email to Wogan to talk about the exceptional Lie algebra case. He told me analysts can compare the J dimension pretty quickly for complex groups up to rank about 7, except that for the case E7, it required a large computer and a day or so on. So it's very slow. And there's still nothing like the RS algorithm for type A case, and our government intention for other classical groups. So from that point, we have a motivation to study the J dimension for exceptional case. And now I'll give a definition. Let A be a K algebra, K some field, and not necessarily associative. And V be a finite dimensional subspace of A, and Vn denoted the linear span of our products of length at most n in elements of A. Then the J dimension of A defined by this super limit. And we take the dimension Vn and take a log and then divided by log n. When n tends to infinity, we take the supreme, and for all the finite dimensional subspace V of A. This is for any key algebra. And it is well known that the Boole definition is independent of the choice of V for a finite generated key algebra with the finite dimensional generating subspace V. And G dimension equal 0 if and only if a some locally finite dimensional. That is, every finite generated subalgebra is finite dimensional. Otherwise, G dimension will bigger or equal to 1. And in 1970, Borgman proved that.
A ver, tiene más que todo. Sorry.
Oh, okay. In 1978, Borgman proved that there is no algebra has G dimension strictly between 1 and 2. And for any real algebra, R bigger or equal to, there is algebra with G dimension equal to R. So now we can see some example. That is, let K be the complex field and A is the polynomial ring, and then M is the finite generated graded King algebra. We denote AQ, that is the homogeneous polynomial of degree Q. Then we compute the dimension of the AQ and take the sum. That is, we consider the subspace generated by expanded by all the homogeneous polynomial that degree less than or equal to n. And then by a combinatorial formula, we can find that the dimension this one actually equals this number. And we take the summation, we found that this summation will equal to this number. This one, the leading term is n to the power n divided by n factorial. And so if we take the logarithm and divide it by log n, we find that the limit will equal to n. So the G dimension only characterize this Lie algebra. It's like that how many elements in the algebra, and the growth rate is like the number of the indeterminate in this algebra. And now we give definition for this dimensional high-weight module. Let G be a finite dimensional simple Lie algebra, and M be a UG module generated by some finite dimensional subspace M0. And UNG is the standard filtration of UG. UG is the universal enveloping algebra. And the G dimension is divided by this one. UNG act on M0 is the subspace of M. And we take a dimension and take a log and divide it by log n. And n tend to infinity. This one actually is independent of the choice of M0. And in 1985, Cross and Lenigan, they proved that when M is the finite generated UG module, and we take the graded module, because after the graded, this module will become SG module. It is commutative. So the G dimension, but we still have the same G dimension. And because it's a commutative module, so we have some commutative algebra method to study it. Let M be a finite generated UG module. We define its assert variety because Bernstein firstly studied this variety, and so sometimes people will call it Bernstein variety. And it because this one is the graded module, so its annihilator is equal to some polynomial. So we take the common zero of this polynomial. So it's like a variety. And if we take denote M0n equal this dimension, and by the theorem of Hilbert and Searle, we find that there is the unique polynomial phi tilde equal phi tilde M0 equal this dimension for large n. The leading term is like this one. Here Cm is called the Bernstein degree. So if we take log and divide it by log, take limit, we find that the G dimension just equal this number dm. Okay, it also equal to the dimension of this variety Vm. There's another definition for the ideal. Let G be a finite dimensional semi-simple algebra and A be a two-sided ideal. Then we take this quotient model, UG quotient by A. This model we take the graded model. It's like this one. So this model has analytic. It's just GRA, and we define its authority. And the previous page, we know the authority is just the graded model, the analytic, and we take the common zero for this polynomial. Because now the analytic is GRA, so we take all the polynomials in this GRA and take the common zero of this polynomial in the dual space G star. So this one is called the authority of this ideal. In 1976, Joseph proved that let G be a complex semi-simple algebra with a kind of sum algebra H, and L lambda be a high-weight UG model with high-weight lambda minus rho. Here rho is the half sum of positive roots, and then the G dimension of this quotient model equal to the dimension of this authority of this analytic ideal, and it also equal to the 2 times G dimension of L lambda. And also proves that when G is the reductively algebra and A be a primitive ideal, then VA equals the closure of a single nilpotent congruent orbits in G star. Because for primitive ideal, it just means that the ideal is the analytic ideal of some irreducible module. And Gelfand also proves that primitive ideal can be realized as some analytic of some high-weight module L lambda. So the study of primitive ideal can be transformed to the study of analytic of some high-weight module. And so here, this authority is also called the analytic variety of the high-weight module L lambda. Actually, for high model, there are many important theories like Lusztig theory related to the high-weight model. That is another motivation for us to study the J dimension of high-weight model. If we use LW to denote the high-weight model with high-weight minus W rho minus rho, here small w is the element in the work group. We denote the analytic for this ideal. Then we X and Y belong to the same Lusztig left cell if and only if AX equal AY. That is the primitive ideal are the same. We say they belong to the same right cell if and only if these two ideals are the same. We say they belong to the same two-sided cell if and only if the ideal have the same authority. That is, the orbit is the same. So the study of the primitive ideal related to the high-weight model and also related to the cell. Further, I talk about the G dimension for high-weight model of classically algebra. I give you some definition for the A function. Let V be indeterminate and H is the Hecke algebra of A. And CW is the convoluted basis of H. We write the multiplication at the combination of other CZ, and HXYZ is like some polynomial in A. And this A function is defined by this one. We take all XY in W and later we fix this thing, and this we fix the we take the max degree of this polynomial, and this one is called the Lusztig A function. And Lusztig told us that when G the complex simple algebra with the kind of sum algebra H and LW be the high-weight model with high-weight like this one, and then the G dimension were equal to the number of positive roots minus AW. Okay. So this is only for the Hive model like LW in this form. And we want to generalize that result to arbitrary Hive model. A weight is called the dominant weight if the inner product of mu with alpha check equal to the positive number, equal to some positive number, and for all positive roots alpha. And weight mu is called the anti-dominant if mu alpha check the parent is not a positive integer. That is, it can be a negative integer or non-integer. And in our first result for type A, this one is for all types. And let's G be a simple complex Lie algebra, and lambda is weight, and double lambda is the integral work group relative to lambda. That is, this subgroup is generated by the simple by some reflection like S alpha, some S alpha. That is lambda and the parent with alpha check equal to Z. And then this double lambda S lambda is the cost system. And we define a function like this one is a function on double lambda. Then we found that the G dimension L lambda for any high weight model L lambda. Then this one equal the number of positive roots and minus A lambda. Here A lambda means A lambda double lambda. And this here this number double lambda is the element in the integral work group, but with the minimal length such that double lambda inverse time lambda is anti-dominant. It seems that we need to compute this double lambda, but our algorithm told us that there is no need to compute this double lambda. We only need the information of lambda. Let me talk about the RS algorithm. For a totally ordered set gamma, we denote sequence SE kilo n gamma, the set of sequence x or length n with xa in gamma. Like gamma, we can take equal to R or C. That is the totally ordered set. We take any sequence. Then we apply in the RS algorithm to this element. We can get a Young table. And the RS algorithm I will talk about later. And there are some examples to show this algorithm. We denote PX, the shape of this Young table. And our result is like this one. This one for the integral weight. That is, we write lambda equal double lambda times mu, because for a unique minimal length element double lambda and unique anti-dominant mu, we write we find that p lambda equal p double lambda. That is, they have the same shape. Then the G dimension equal the number of elements in phi plus minus a double lambda. Actually, the method only use RS algorithm. Let me show it. Because here G equal for type A, and for any weight we write it as T1 to Tn, and we divide this lambda into some subsequence. And for every sequence we have a Young table. Let lambda y be a maximal subsequence of T1 to Tn, such that TAK are congruent to each other by Z. And then the Young table associated to this sequence is the Young table in this set P lambda. And if we weight the Young table is like some boxes. And then we define a number AY, that is A minus 1 times YA. And here where is the number of entries in this S row, and it also equal to this one, CA times CA minus 1 divided by 2, and CA is number of entry in the S column. And then we define AP lambda equal the summation of this AY. we find that for type A case, the G dimension equal to the n times n minus 1 divided by 2 minus this number. This number is our AP lambda. So we only use the information of lambda and the RS algorithm to compute our G dimension. Let me show you this example. For example, we have a lambda like this form. We divide it into several subsequences like this one, and this one. For any two elements in the sequence, subsequence, so any of them have an integer difference. So the RS algorithm, like this type, because the first number is 3, and the second number is 2. So first we put a box and put a 3 in it, and then 2 is smaller than 3. That is, in the first row we take we replace 3 by 2, and then 3 is moved to the second row, and then the next one is minus 1. Similarly, we take the first element, which is bigger than the new element, that is 2. So this one is minus 1. And 2, we put it in the second row because the 2 is smaller than 3. So we move 3 down. And then we get a new tableau. And then next one is minus 1. God, we want to take a minimal element, so we regard the second one, minus 1 is bigger than the first minus 1. So because this one is bigger than this one, because in the first row there is no element bigger than this new element, so we put this new element in the right side. That is, we have maybe I put it here, minus 1, minus 1, and then 2, then 3. Okay, we get this new box, new diagram, and then the last one is 0. So we still the 0 in the right side. So this is the RS algorithm. So we get this Young tableau, and similarly for this one, get this tableau, because this one is just one element, so it's just one tableau. This one algorithm called the Robinson-Shented insertion algorithm, or simply we call it RS algorithm. So for every Young diagram, we can get a number like that, because if this column there's only one element, so it only give us 0. So we only count the column with more than one box. Okay, so this one will give us this number. This one will give us this number. Okay, so finally we can get the G dimension for this case. So our algorithm is very simple. You only need to know this RS algorithm. And for type BCD case, the algorithm is later difficult because it will use the representation of the work group of type BCD. Yeah. So I will talk about the routine A function for type B. We denote lambda like this tablet. Here lambda and mu are non-negative integers and strictly increasing in each row, and their summation equal to this one. And the equivalence relation, because like this one, we put 0 on each row and add 1 every element. The set of this equivalent class is called the Lusztig B symbol. This B symbol is actually it can characterize the representation of the work groups of type B. And for this B symbol, we can define Lusztig defined the A function like this form. And for work group type B, we can realize it as a subgroup of the permutation of S2n. Permutation on these 2n elements such that WA will equal minus W minus A. And we use some generator says S0 equals 1 max to minus 1, and SA, that is A max to A plus 1, and SB equal to this set. Then this one will give us the cost system. And from boundary working, we know that there is another map that is from B symbol, we can get D symbol. That is, we only add 0 on the second row, and for other elements with plus 1. This element is like type is the symbol type D. Here I didn't give some detail of the definition for type D. It's like we have the same element in the first row and the second row. And how to get a symbol from work group element? That is, we write element and then we write W bar, and then because W1, Wn minus 1, Wn will give us the element of W, and we write it symmetrically like this one. And this one is a sequence with 2 n elements. Then we use RS algorithm, we can get a Young table. This table contains several rows, and this row will give us a partition of 2n. And we can always assume that R is odd number, let's say 2m plus 1, by adding 0 if necessary. Then we take data like this one, that is the PA plus A, okay, plus A minus 1, okay. This one gives a sequence strictly increasing integer, and then we can get a symbol. That is, we take the even number in this data, and then divide it by 2 and put it in the first row. And then for the odd number, we minus 1 and divide it by 2 in putting them in the second row. So this is the B symbol. And I forget that here is the definition for the D symbol. That is, we have a table like this one, and lambda mu non-negative integer and strictly increasing in each row, and with this summation. And also we have equivalent relation. That is, we can change the order of the first and second row, and then we put 0 on the first, on the left side, and then plus 1 for every element. This set is equivalent class under this equivalent relation called the Lusztig D symbol. D symbol will characterize the representation of the work group of type D. Also, Lusztig defined a function for this symbol. At the beginning, we don't know that how to compare a function for work group of type BCD, and because we only found that for the symbol, they are definition for the A function. So we asked Lusztig, is it true that we can compare the A function from work group? We can get a symbol, and then we compare the A function for the symbol, and then we can get the A function for the work group elements. They said yes. So we found we can get the result like this one. I cannot move it. Okay. That is okay. This is for type D case. We also had the realization of the work groups. It can be realized as this one, because it's a subgroup of permutation on these elements. But this is for type B, Wn, and for type D, we use Wn prime. is the subgroup of Wn, and there's a restriction that the negative integer in this set is even. Okay, we use u equals 1 maps to -2 and SA, and then we get a generating set. This one is also a cost system, and from type B symbol we can get D symbol, that is Buffer-Wagon result. And because we didn't find the reference for the computational A function, so we'll give a proof for this computational A function. From this for type B, type D case. For type B, type C is similar. Here we use A function, that is it can be computed like this one. It's like I move here. Okay, we can form a workgroup element type D. We can get a symbol type D. Firstly, actually we get a symbol type B, and then by the map D we can get a symbol type D, and then we can compute the A function for this symbol. Then we combine these two maps, we can get the computation of the workgroup elements. This is for the type of BCD case, it's similar. But later on we found that we can get some more simple method to compute the A function. Here we introduce the even and odd table. That is for Young diagram P. Young diagram is like Young table, but only record the shape of the Young table. We use KL to denote the box in the case row and S column. We say the box KL is even, respectively odd if K plus L is even. Like this example. This one is 1 plus 1 is even. This one, the first row and second column, so this one is odd. Okay. So we denote this number PA even, number of even boxes in the S row, and PA odd, number of odd boxes in the S row. So we can find the number. It can be computed by this formula. Here, this one is the largest integer such that n less than or equal to a, and this one is the smallest integer such that n bigger or equal to a. So we can denote P even like this sequence and P odd like this sequence. And then for a sequence X, we denote X bar like this one. Symmetrically, we write in the right side. And the A function, this is for type A. I think you can, we get this A function by using RS algorithm. And similarly, we can get the A function like this one. This is for type BC case, this is for type D case. Because in our algorithm, for type A case, we don't need to compute the number double lambda. Actually, for type B, type C case, type BCD case, we still don't need to compute the number double lambda. You know, at the beginning, we write lambda equal double lambda mu for unique minimalist element double lambda, and a unique anti-dominant mu, and P double lambda is the Young table, and P lambda bar equal P bar W lambda. For this one is for type BC case, and sometimes for type D case we may have this one or this one, because we don't know double lambda or double lambda S0, which one is element in type D case. So there are two choices that depend on double lambda or double lambda times S0, which one belong to Wn prime. Okay. But we don't need to care about this point. We only need to compute the for type BC case. We only compute the all the elements in each row. And for type D case, we need to compute the even boxes in each row. Okay. So P lambda bar, this one is only use the RS algorithm. It's like a type A case. So it's more similar than Lusztig's formula. And for the non-integral case, because the integral work group is more complicated, so we need some notation, some more notation. Here, lambda is the set maximal subsequence of x, such that each pair of entries x has an integral sum or difference. And lambda 1 is the subset of lambda consisting subsequent with the integral integer. And lambda 2 is the subsequent with the half integral. Actually, there is only one sequence in lambda 1 and only one sequence in lambda 2. So for other subsequences, we denote them by lambda 3. And for everyone in lambda 3, we can obtain two subsequence x1, x2. That is the difference of any two entries in s1 or x2 is the integer. But the elements in s1 and x2, their summation is the integer. So we divided them into two parts. And we define, for this x, we define a new one, x tilde. And we put them like this one, symmetrically. We change the order in x2 and take the negative of them. And our algorithm for type BCD is like this one. For every element like type B, in lambda 1, lambda 2, there's only one sequence. We can get a function by using our integral formula case, like this one. We use all the boxes. And for type A case, we have the result in type A case. Okay. For lambda 3, we have the result in type A case. This is for type C. This is for type D case. Okay. So we only need to use the RS algorithm to compute the J dimensions. And we still have a web page to realize our result. Let me show you. Okay. Like this one. Let me see. You can put any number is infinitesimal. That is, lambda is intentional character. We put a lambda here, and for any type, you just calculate is T dimension. Because at the beginning we want to compute the analytic variety is some nilpotent object closure. So this web page contains more information. We can divide the lambda into several subsequence, and for every subsequence we can get a diagram. And for every diagram we can get the some partition, and then we can get the orbit. And actually we can get the J dimension here. Okay. Let me continue. Yeah. So now we can talk about the ephemeral case. For this one, because the computation of the A function for work groups, the computation is more complicated. At the beginning, we don't find any reference to compute the A function for exceptional type Lie work groups. But finally, we find that we can using this PyCox. This one is designed by, I think maybe Gecker. Yeah. From this PyCox, we can get the some information like character and the value of A function. Yeah. But in his paper, the notation is a little different. This is the E7 case, like 2 actually means S3, S alpha 3. This 3 equal S4. This 1 equal S2. 3 equal S4. Okay, it's like multiplication. We write this workable element in the same simple reflection. So we can get a function by using PyCos. This let me see example. Let me see. Like this one. Let me see. Okay, like this one. You can see this is very fast. It's less than 1 minute for E7 case. You can get a value. But for other cases, like type E8, it may take about 2 minutes. For E6, maybe 1 minute, but it's still very fast, I think, than Atlas. Yeah. Okay. Okay. Well, here we define another algorithm called the PAR algorithm, that is a positive index reduction algorithm. From this algorithm, we can get the W lambda. Here we write a row at half of some positive rows and alpha j is simple rows. You can write it as linear combination of W omega k. And for n lambda, we write lambda as a linear combination of some omega a. And k is this number. Here lambda is the integral weight if and only if all the coefficients are integer. Yeah. The lambda is the integral anti-dominant weight if and only if all the coefficients k negative or positive, they are negative integer, they can equal to 0. And here from lambda, if lambda is anti-dominant, here W lambda equal to identity. If lambda is not anti-dominant, from this lemma we can see that there are some coefficients k. Maybe we take some one of them, that is this number will bigger than 0. So we take the largest index, we denote it by A1, such that K1 is the positive integer. And then we take SA1 act on lambda, and we can get this number. We can see that the coefficient of omega A1 in SA1 times lambda will become to minus Ka1. So it's not a positive integer now. We continue this process and until all the coefficients of omega A are not a positive integer. This process will stop after final steps. We multiply all the simple reflection SA appeared in this process. We can get our W lambda. For example, we write lambda in this form. It's the integral weight of type E7. And we write it as a linear combination of fundamental weights in this form. We only care about the coefficient, so we denote it like this sequence. And the largest index with the positive element is this one, 3. So the A1 is equal to 3. So we take S3 time act on lambda, we get this one. And this one, we see the largest index with positive integer is A2 equal 4, and we take S4 act on this one. So then we continue, we find that the largest index is the second one, that is S3 equal 2. So we S2 times this one. And then finally we find that the A4 equal 4. So we multiply S4 on the left side. And then we find that all the coefficients are negative integer. So it's antidominant. So we multiply all the elements, simple reflection in this process. We get double lambda. Here the order is we change the order in the sequence that is S3, S4, S2, S4. Then we use pi cos. We can get the A value equals 3. Let me here. This is our number 2, 3, 1, 3. So the A value is that is 3. We continue. Sorry. So we use pi cos to compute this A value. Actually, this algorithm is the reformulation of some algorithm for numbered game. This numbered game is studied by Barney and Brenty and Erickson. They studied this algorithm, this game for the cost groups. So now, how to compute the A function for integral weight or the non-integral weight? Here we have some theorem to reduce our algorithm to the integral case. If we have to root system, we can F is the isomorphism. We use F to denote this isomorphism for the Gardner-Summer algebra and the dual space. Then we have isomorphism for the integral root system, and then P0 is some system of P, and they have the same rank. And then lambda prime is the image, is the integral weight of type P0, and then we have the same A value. If rank of P0 is less than the dimension of effect, we still we denote the lambda bar prime is the image of this one. Then we have the A value. In general, our algorithm is like this one. We divide the integral root system into products or irreducible root system, and we use the phi to denote this isomorphism. And then for each phi, we have a simple system, delta A, and then delta lambda is the same system phi lambda, like alpha 1 to alpha n, and then it is the product like some delta lambda A, and we write lambda restricted to this sum algebra case. So we denote lambda prime is the image like this one. Then we find that if phi is the classical type, then we restrict to lambda bar prime to phi. It's like Euclidean coordinates, and then we can use our RS algorithm to compute this the value of this A function without finding out this W. And if some of them is the exemplar type, you can find this W by using the PAR algorithm. But here we should use pi cos. And then we can put the summation of these A value. We can get our A function. And this is an example of type F4. This is our lambda, the infinitesimal character. Then phi lambda is some system with some simple rules like this one. I put them in this order because the first three rules correspond to the simple rules of B3, and the latter one correspond to the simple system of A1. And we find that because the standard simple system B3 times A1 is like this one, this form, this one. And so we define isomorphism map from phi lambda to B3 times A1. That is alpha 1 to beta 1, alpha 1, alpha 2, beta 1, alpha 1 to beta 2, and this root map to beta 3, and alpha 4 map to beta 1 prime. Then we denote lambda bar prime is the image of F lambda. And then we find that lambda bar prime retreat to B3 equal to this one. Because omega I is standard in the case of B3, so we can write it in the Euclidean coordinates like 2, 0, 1. Then we can use our algorithm, RS algorithm, to compare to the A value of this one. And lambda bar prime retrigger to A1, we get omega 1 prime, that is this one. So we can get A value by using RS algorithm. And then we might we combine the we commit the summation of these two values, we get the Zig dimension. Okay, then we can get this one. Also, we have a web page to realize our algorithm. That is this one. Let me see. You see, or maybe I made a mistake. Maybe not this one. Is yeah, this algorithm. This one here. Like here you should insert the rank of this algebra, because for En there are several ranks, so you can compute the Zig dimension. Here the information for the integral root system and for the every component we can get the coordinates. Then we can get the character and the A value. Then we can get the Zig dimension. So you only need to know this web page to get the results. It's very faster than Atlas. Okay, there are some references. The first one is our algorithm for type A case, and then for type BCD case. And for the ephemeral algebra, we are still working on it because we want to compute more things, that is another variety. So it's not finished because the algorithm is finished because the web page is not finished. Okay. Okay, I stop here. Thank you.
Thank you. Thank you, Dr. Bai. So we have 5 minutes for questions. Any questions or comments? I have a question. So this is only for classical simple Lie algebras, yes?
No.
Including exceptional ones. Yeah?
This web page is for the exceptional case. We have 2 web pages. This one is for the classical case.
And is it possible to consider similar questions, similar notions for other class of algebras, for example, for Leibniz algebras?
I don't know. I only care about the simple Lie algebra case. The classical.
And what about infinite dimensional Lie algebras? Is it possible to consider?
I don't know.
Okay. Thank you. So, more questions, comments, please.
Hello.
Yes.
Yeah.
Hello, Antonio.
Prof. Bai. Yeah. Very interesting talk. Thank you very much. How about these all are going on over complex numbers? Is any interest to do the same over other fields? Any issues come out in it? Thank you.
For other fields, it may be more difficult. Like finite field, some people care about the J dimension, but it's more difficult.
Okay. So if there's no more questions, let us thank Professor Bai for a very interesting talk.
Thank you.
Thank you. Thank you very much.
Thank you.
So in a few minutes, we have a second talk.